Hello, I am Alvaro Chavarria, Assistant Professor of Physics, and I would like to welcome you to this spring's Frontiers of Physics lecture. The Frontiers of Physics lecture series brings to the University of Washington and the Seattle community world-class scientists to explain to you the most exciting developments and discoveries in physics. The biannual lecture series started in 2015 and has so far showcased 10 outstanding presentations by top figures in the field, including 5 Nobel laureates. The topics cover a wide range of phenomena from the early universe to the present, from the extragalactic scale to the microscopic role of quantum mechanics, from abstract theoretical concepts to the subtleties of otherwise familiar ideas. The lecture series is only possible by the work of a diverse committee with members of the faculty and our community. After a hiatus in 2020 because of the unfortunate global pandemic, we resume today with our first online lecture. We hope to return Frontiers of Physics lectures to Kane Hall on UW campus for next year's autumn and spring quarters. This evening, it is my pleasure to introduce Nobel laureate Dr. William D Phillips, who will be presenting about the redefinition of the metric system in terms of the fundamental constants of nature, an achievement that embodies the universal character of science and brings us one step closer to the dream to make science accessible to all. William D Phillips received his bachelor's degree in physics from Juniata College in 1970 and his PhD from the Massachusetts Institute of Technology in 1976. He shared the 1997 Nobel Prize in Physics for the development of methods to cool and trap atoms with laser light. He has spent most of his illustrious career at the National Institute of Standards and Technology, or Nist, where he founded the Laser Cooling and Trapping Group, and is also a founding member of the Joint Quantum Institute between Nist and the University of Maryland. His research group has been responsible for developing some of the main techniques used today for laser cooling and cold atom experiments around the world. Their achievements include the first electromagnetic trapping of neutral atoms, reaching laser cooling temperatures within a millionth of a degree of absolute zero, and confining atoms in optical lattices. Atomic fountain clocks, which are based on the work of his group, are now the primary standards for timekeeping in the world. Among his current research directions are the use of ultra-cold atoms for quantum information processing and the quantum simulation of important physical systems. Following today's lecture, we will have a Q&A with Dr. Phillips, hosted by my colleague, Professor Kaimei Fu. I encourage you to submit your questions as they occur to you in the YouTube chat box or by email to fpls@uw.edu. You can find the Q&A instructions and information on how to support the University of Washington's Department of Physics in the video description just below. Please join me in remotely welcoming Dr. William D. Phillips.
Thank you very much, Alvaro. It's a great pleasure for me to be here to talk to you about these revolutionary reforms to the metric system. As you've heard, I'm from the Joint Quantum Institute, the University of Maryland, and Nist. And at Nist, I'm part of this laser cooling and trapping group, whose leader is Gretchen Campbell. Paulette, Trey Porto, Ian Spielman, and Ida Tietzinger are the other members of that group, and it's a great pleasure for me to work with them on a daily basis. So Nist is responsible for a lot of the reforms that I'm going to be telling you about today. And another organization, the International Union of Pure and Applied Physics, has been a longtime supporter of the international metric system. And as a member of one of its commissions, I've been trying to spread the word around the world about the changes to the metric system. So why am I talking to you today about the metric system? Well, the reason is that on the 20th of May, 2019, just 2 years ago, on what is World Metrology Day, we experienced the biggest revolution in measurement since the French Revolution. The French Revolution is what brought us the metric system in the first place. So this international system of units, the thing we use to measure essentially everything that we measure, has been radically altered. And the nature of that change is a change to what are known as the base units, the units on which all other units are based. The kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela are the base units. And now, because of these revolutionary changes, every one of those units is defined by fixing the value of a constant of nature. Now, to understand how it's even possible for such a thing to be true and how we can go about doing it, I would like to, with apologies to the late, great Stephen Hawking, bring you my version of a brief history of time. So what about time? Since we've had seconds, a second has been 1 day divided by 24 hours per day times 60 minutes per hour times 60 seconds per minute. So a second was 1 day divided by 86,400. Now, the problem was that by the time of the turn of the century, around 1900, we realized, because of the fact that we could make clocks that were even better than the Earth, we realized that that length of day was changing. But of course, the length of day couldn't change because it was always 1 over, it was always 86,400 seconds. And yet we knew that it was changing because we had clocks that were more stable than the Earth. One of those clocks from about the middle of the 20th century was the very first atomic clock made at Nist, or at the National Bureau of Standards, which was what it was called back then. It was actually a molecular clock. And the thing that's important to understand is that while the Earth may change, that is, the rate of rotation of the Earth can change due to all sorts of things, the friction of the tides, the changing of ocean currents, earthquakes that redistribute the mass of the Earth. All these things can change the rotation rate of the Earth. But atoms and molecules don't change, or at least as far as we know. And so making a clock that has a ticker that is atoms or molecules gives you a clock that is really, really good. And these clocks were able to show that the Earth's rotation was changing. Here's a clock that was made a little bit later in 1955 at the United Kingdom's National Standards Laboratory using cesium atoms as the tickers. So these clocks had been operating for more than a decade in 1960. They were much better than the rotation of the Earth. And so it was clear that we had to change the definition of the second. We had a definition of time that itself was not constant in time, and that was just not tolerable. We can't have a measurement system where the basis of the measurement system is something that changes from time to time. And so they had to redefine what a second was. And so what with this wonderful new atomic clock that was much better than the rotation of the Earth, in 1960, they redefined the second to be a fraction of the year 1900. What were they thinking? It's true enough that the year 1900 never changes, but it's not exactly readily available for measurement today. Well, not only did they make a bad choice by trying to redefine the second astronomically, they actually chose the wrong number. They chose the number that was a fraction of the year 1900. They chose a number that was the average of the mean solar day over the past some years. It wasn't equal to the mean solar day at the time. And this is why we are plagued by leap seconds today. And if you don't know what a leap second is, ask me, and I'll be happy to tell you about leap seconds. But this is the result of them not making a good choice. Well, finally, in 1967, they got smart, and they defined the second to be a certain number of oscillations of a cesium atom. Some 9 billion oscillations of a cesium atom became the definition of the second. And over time, these cesium atomic clocks just kept getting better and better. At the time of the clock that I showed you in that picture from the United Kingdom, they were good to about a part in 10 to the 11th. Pretty good. But by the mid-1990s, they were good to about a part in 10 to the 14. But they stalled at about a part in 10 to the 14 because of the fact that the cesium atoms were moving so fast. Well, one of the things that I've spent most of my life doing, which I'm not talking about today, namely laser cooling, was able to make those cesium atoms move more slowly. And today, we have atomic clocks like this one that you can see here. Don Meekhoff and Steve Jeffords laser cool cesium atoms and toss them up in a vacuum. They come back down, and these clocks are good to a few parts in 10 to the 16. This is the most accurately measured quantity in the International System of Units, the Système International, or the SI as we call it. So the story here is that we had a definition of time that wasn't very good and was changeable. That was based on the rotation of the Earth. And because we had a better technology for measuring time, we changed the definition to something that doesn't change, something that's a constant of nature, namely the frequency of oscillation of a cesium atom. Okay, so that's time. The next thing is length. So here comes a short history of length. Now, time was important, but length was really important historically because length involved things like commerce and construction. The usual length standard in ancient times was the human body. A foot was a foot. A cubit was the distance between your elbow and the end of your finger. A fathom was the wingspan of your two arms. This was great because you always had your standard with you. But it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might be buying a smaller length of fabric than you had expected. And so, realizing this problem with consistency, people came up with a solution. And the solution was that we should choose one particular body, the body of the monarch or the pharaoh. In this case, the royal cubit was the length of the pharaoh's forearm. And in ancient Egypt, they used that as the standard of length. Now, the problem was that the pharaoh is not always available. When you're building the pyramids, you don't necessarily have the pharaoh out in the field to provide a unit of measurement. So they did something which is remarkably modern. They made an artifact, a stick made out of granite that was the length of the pharaoh's forearm. And that became the primary standard of length for all of Egypt. People out in the field building the pyramids had wooden versions of this royal cubit that they had to calibrate against the stone cubit. So they would take it out and use it. And if it got worn, they would come back, calibrate it, readjust things. And if you didn't calibrate it every month, the penalty was the death penalty. These people were really serious about metrology. And it paid off. The baselines of the pyramids are consistent to a fraction of a percent. The base of the pyramid is square to 12 arc seconds. These are really well-made structures. And the reason is because they were really serious about length metrology. And that idea of making an artifact is something that became quite widespread. In the Middle Ages, you had it, it was very common to have an artifact length standard cemented into the wall of a city square so that everybody would have access to the standard of length for that town. Here's a picture of the fathom, the standard fathom, in the town of Regensburg. And you can see by comparison to a random tourist who isn't exactly random, she's the spouse of a metrologist, as it turns out. This is a pretty good place to buy things by the fathom because it's quite a large fathom. But if you were to go into surrounding Bavaria, you would find a different standard of length. This was a problem that was common throughout the medieval world. that standards of length were not consistent from one place to another. It was really annoying, but it was extremely common. Now comes the French Revolution. The philosophy of the French Revolution: liberty, fraternity, equality. And as part of that philosophy, they wanted to have a standard of length that was available to everybody, something that was different from the standards that had been used by the old regime. They wanted something entirely new. And they called that standard of length the meter. And they defined the meter to be equal to 1/10,000,000th of the distance between the North Pole of the Earth and the equator along a meridian that goes through Paris. That was the definition of the meter. Well, how did they use that? Well, they sent out teams of surveyors to survey the distance between Barcelona in the south and Dunkirk in the north, and then they extrapolated that distance to the entire meridian between the North Pole and the equator. And they made this measurement in terms of the old system of units and brought their measurements back to Paris. And now people realized that, well, it's wonderful. We now know what the meter is, this new standard of length, in terms of the old standards, but how are we going to use it? So they did the same thing that the ancient Egyptians did. This was just to emphasize that these French revolutionaries had this dream of making a measurement system that was going to be good for all time and for all peoples. And this medal that is shown here was cast to commemorate that idea. And you see this mythological creature is actually measuring the earth. And that's exactly what they did. They measured the earth so as to create this new standard of length. But like the ancient Egyptians, they found that it wasn't so convenient to have the standard of length be related to the earth, because it wasn't so easy to resurvey the earth every time you wanted to know what a meter was. And so they took the results from these surveyors that had determined what the meter was in terms of the old standards of length, and they made a new artifact, just as the ancient Egyptians had made an artifact based on the pharaoh's forearm. And this is a picture of what's known as the meter of the archives. It's a bar made out of platinum, and its end-to-end distance is a meter. And from 1799, this became the official legal meter for all of France, very much in the spirit of what the Egyptians did. So we can see that what the Egyptians did was remarkably modern. Some decades later, the entire world agreed that they would adopt the meter as the standard of length. In 1875, a group of countries from all over the world convened in Paris and signed a treaty called the Convention du Mètre, the meter treaty. And they agreed that they would adopt the metric system. They agreed that they would use their resources to support a laboratory called the International Bureau of Weights and Measures to maintain these standards. And one of the things that they agreed was that they would make a new standard of length. This thing was called the International Prototype of the Meter. And instead of being a rod whose end-to-end distance was 1 meter, it was a bar on which there were 2 scratches. And the distance between these scratches was the definition of a meter. Now, this was an advantage compared to the end standard, because the problem with an end standard is that in order to determine its length, you have to touch the end. But with a line standard, that's what this is officially called. With a line standard, the distance between these 2 scratches is something you can determine by using a microscope attached to a traveling screw thread, and that's the way people made length measurements. That was wonderful, except for the fact that almost as soon as they established this new standard of length in 1875, they realized that they had a much better way of measuring length. In the 19th century, people discovered that light was a wave. Newton had taught that light was a stream of particles, but it turned out that wasn't true. Light is a wave, just like a sound wave or a water wave. And what that means is that two beams of light can interfere with each other to produce either more light when the waves line up or less light when the waves don't line up, so that they tend to cancel out. And I've shown here a cartoon of a device called an interferometer that does exactly that. You send some light into this device, and it comes onto what we call a beam splitter or a half-silvered mirror. And some of the light is reflected from this mirror and goes that way. And some of the light is transmitted by this mirror and goes this way and hits another mirror. Whoops, sorry about that. The light reflects from this fixed mirror, goes back, and some of it reflects over here. The light that went this way reflects off this movable mirror, and some of it comes back and interferes with the light that came off of this mirror. And in the place where the two waves line up, you get a bright region. And in the place where the waves are out of sync with each other and cancel each other out, you get a dark spot. When you move this mirror by 1/4 of the wavelength of light, and 1/4 of the wavelength of light is a fraction of 1/1,000,000th of a meter. If you move it just 1/4 of a wavelength of light, this spot changes from being dark to being light. So it's easy to see. That means that this device can easily measure distances that are much less than 1/1,000,000th of a meter. Now imagine trying to measure the distance between two scratches, two better than 1/1,000,000th of a meter. It's a scratch. It's many millionths of a meter wide, and you're looking at it with a microscope that cannot see things that are smaller than 1/1,000,000th of a meter. And so people realized that they had this better way of measuring length, and they started to measure lengths in terms of the wavelength of light. This was not the official definition of length, but it became the de facto definition of length that was used for decades before they finally changed the definition. So finally, in 1960, the year the laser was invented, they redefined the meter to be a certain number of wavelengths of the light that comes from a lamp that has krypton gas in it. And here's a picture of that lamp. And when you put electrical current through this lamp, it glows orange. And the wavelength of that orange light became the new definition of the meter. So here we see something very similar to what happened with time. We had an old definition and then a new technology that allowed us to measure things a lot better than the old definition being the distance between two scratches. And now we had a better technology, an interferometer, and light from a lamp. And so they redefined the meter in terms of this new technology. But almost as soon as they had this new definition, we started to have lasers that had light that was so much better than the light coming from the lamp. And by better, I mean so much purer in its color that there's only one wavelength coming out of that laser compared to the mixture of wavelengths that comes out of a lamp, that people started using laser light as the de facto standard. Again, we have a new technology that's better than the old technology, and it was clear that just as happened in the past with time and with length, we needed to change the definition of length. The definition of the meter needed to be changed. Now, the obvious choice would have been to change the definition of the meter to be a certain number of wavelengths of the light coming out of this laser. It was an iodine-stabilized helium-neon laser. Helium-neon gas makes the laser light, and then you lock the wavelength of that light to an iodine molecule. And people were using this as the de facto standard. Everybody used it as the non-official standard of length. And the obvious choice would have been to make it official. Fortunately, people did not make the obvious choice. Fortunately, instead, people made a brilliant choice, a beautiful choice. They defined the speed of light. They fixed the value of a constant of nature. How can you do that? Well, here's the new definition of the meter. The meter, as of 1983, the meter is the length of the path traveled by light in vacuum during a time interval of 1 over some number of seconds. In other words, some fraction of a second. It's the distance the light travels in a fraction of a second. And you see, if you define the meter to be the distance that light travels in a fraction of a second, you've defined the speed of light. Now, the wonderful thing about this is that we have this universal expression, the wavelength of light times its frequency. Remember, light is a wave, so it's oscillating back and forth, just like any other wave. And the frequency of that wave is the frequency of the light. The wavelength times the frequency is equal to the speed of light, and that's true no matter what the light is. So if somebody uses a different kind of laser, if we've defined the speed of light, we know what its wavelength is. So immediately, as soon as you measure the frequency of any kind of light, you immediately know its wavelength, and you can measure things in terms of that wavelength. So if somebody makes a better laser so that its wavelength is more pure, this equation still works. The definition is still good. If somebody invents a way of measuring the frequency of light better, this definition is still good. And people did make better lasers, and people did develop ways of measuring the frequency better, and we did not have to change the definition of the meter. All of those improvements were automatically incorporated into this definition. So here you see something really beautiful happen. We started with a definition of length based on an artifact, the distance between two scratches, which depended upon where you decided the middle of the scratch was. Not a very good standard of length. We changed that to the properties of the krypton atom. And then we changed it to a more universal property, the speed of light. And the beauty of this is that we should never have to change this definition again. This definition, in my opinion, is both brilliant and beautiful. And on the 20th of May, 2019, we brought this same brilliance to the definition of the kilogram. And for that matter, to the definition of the ampere, the Kelvin, the unit of temperature, and the mole, the amount of chemical substance. So why did we have to do that, and how? Well, in order to tell you that, I'm going to bring you now a light history of mass. So here is a picture of some artifact mass standards from ancient Babylonia. One of these stones, I forget which one, is called a shekel. You may have heard that as a standard of mass. And these worked very well, as artifacts do, but they suffered from the same problem that all of these other artifacts do. They're not the same from one place to another. You go to another place, another country, they're going to have a different set of artifact standards, and it's a mess. The French revolutionaries recognized this as well. They recognized that, just as in the case of length, that they needed a new standard of mass. And thinking about how they had come up with this new standard of length, the meter, they came up with a mass standard that was based on it. The new revolutionary mass standard was that this new unit, the kilogram, was the mass of 1 liter of water. 1 liter of water is a cubic decimeter. That is a cube 1/10 of a meter on a side. That's 1 liter, and the mass of that water is what we call 1 kilogram, or at least it was at the time of the French Revolution. But just as we've seen again and again, this definition, while it has a certain beauty to it, everybody has water, we now have a good definition of the meter, it wasn't very practical. It was hard to determine what the mass of 1 liter of water was. The density of water changes, the water sticks to surfaces, it wets some surfaces and it doesn't wet other surfaces. And so to avoid these kinds of problems, they created an artifact, just as we've seen again and again. And here am I holding that artifact, that small platinum cylinder that you see inside that case I'm holding is the kilogram of the archives. I was visiting the archives and they let me hold it. And in 1799, that object was deposited in the archives of France, and it became the standard of mass for all of France. And some decades later, at the time of the Convention du Metre, at the time of the International Meter Treaty, they decided they would make a new mass standard, the international prototype of the kilogram, made out of platinum iridium. And there it is. You can see it under these 3 glass jars. And this was the artifact which defined mass for the entire world until 2 years ago. The definition of the kilogram was that the kilogram is the mass of the international prototype of the kilogram. Now think about this. It's the 21st century, 2019. The unit of mass is an artifact, a piece of metal made in the 19th century based on an object that was made in the 18th century. It was made to be equal to the mass of that kilogram of the archives. The fact that in the 21st century, we're using something based on an 18th century artifact is such a scandal that American newspaper comic strips were making fun of it. So in this comic strip, a little girl asks her science teacher, isn't it true that the meter was redefined in terms of the speed of light? As we've seen, that's exactly right. The old definition based on the Earth was not very good. And then she asks, and in the same way, we've redefined the second. So it's no longer based on the length of the day, but it's based on the oscillations of the cesium atom. The science teacher is pleased with her. And then she says, why haven't we changed the definition of the kilogram? The original and official definition is still the mass of the international prototype of the kilogram, a lump of stuff. What if somebody sneaked in and shaved off a piece? Well, this so disturbs the science teacher that he has to go and lie down, and we see that the little girl has achieved her aim of winding up her science teacher, something I'm sure that none of you have ever wanted to do. But the point is that while nobody has in fact sneaked in and shaved off a piece of the international prototype of the kilogram, any change of its mass would change the mass of everything else. And it appears that it is changing. Here is a plot of the mass of the international prototype of the kilogram relative to other copies that were made at the same time. And all these copies were made in an absolutely identical way. So they should have been all the same. But you'll notice that all of these other copies are getting heavier compared to the international prototype of the kilogram. Well, it doesn't take that much imagination to figure out that maybe it's the international prototype of the kilogram that's doing the changing. But of course, the international prototype of the kilogram cannot change because it is by definition a kilogram. So it seems like the entire universe is getting heavier with time, and that just doesn't make any sense. Something has to be done. We have to fix this kilogram problem. It is indeed a scandal. And the way to fix this scandal is to use the same kind of brilliant and beautiful approach that we used for the meter. The approach for the meter was we defined the speed of light. What are we going to define in order to fix the kilogram problem? Well, in order to see that, let's look at what I feel confident is the most famous equation in history, namely E equals mc squared. What does this mean? It means that the energy of an object at rest is equal to the mass of that object times the square of the speed of light. Now, here's another equation, not quite as famous, also for energy. It says that the energy of a photon, a particle of light. Now, why am I saying a particle of light? Didn't I just tell you that Newton said that light was a stream of particles? But in the 19th century, people discovered that light was a wave and not a particle. True. But in the 20th century, Einstein discovered that light was both a wave and a particle. It's one of the most wonderful mysteries and beautiful features of the theory of quantum mechanics on which we're basing these new changes in the metric system. And so we have a particle of light, which we call a photon. Its energy is equal to the frequency of the light. Remember, light is still a wave, and so it's got a frequency, times a constant called Planck's constant, which is a really small number. What does it mean to say that the energy is equal to h times the frequency? It means that if I had well, first let me solve this, put these two equations together and solve for the mass. And the meaning of this is that if I had an object like a nucleus that emitted a photon, say in the form of a gamma ray, and I could measure the frequency of that gamma ray, if I fix the value of Planck's constant, and I've already fixed the value of C, it means I know what the change of the mass is in kilograms. Now, that's not the way we actually do it. We could, in fact, weigh photons this way, and people do. It's just that at the moment, we can't do it well enough for the kind of metrology needs that we have, the accuracy with which we need to measure masses. So we don't do it that way. Instead, we do it a way that was taught by this wonderful fellow, Brian Kibble, who invented an electromechanical device, which we know now as the Kibble balance or the Watt balance. And in this little movie, I'm going to show you how it works. So first, I want you to recall how we weigh things ordinarily. Let's say that I have an unknown mass here on this side of the balance. If I want to know how much it weighs, its mass, I mean to say, then I put known masses on the other side. And I keep putting known masses on the other side until the balance balances. And that's how we weigh stuff. You've probably done this any number of times. Now I want you to imagine a different way of weighing things. Let's imagine that instead of putting a known mass on this side, I have a coil of wire. And that coil of wire is in the field of some magnets. Now, if I can measure how much current is in this wire, and I can measure where that current goes in those wires, and I can measure this magnetic field represented by these red lines, and measure the strength and the direction of the magnetic field. If I could measure all those things, I could calculate what the force is on here, and then I adjust it until that force balances the force due to this unknown mass. And if I can measure the acceleration of gravity, which is not so hard to do, then I would know what the mass was. Great. The problem is that all those things about measuring this current, knowing where the current goes, knowing what the magnetic field is, none of those things can be done well enough to make this a good way of doing things. But here's where Kibble comes in. Kibble was a genius. And what he said was, okay, we can't measure those things. Let's measure something else. Take that coil, and instead of putting current through the coil, take the leads of that coil and connect those leads up to a voltmeter. Now, if you move this coil, it's sort of like a generator. You move a coil of wire in a magnetic field, it generates electricity. So what's going to happen is it's going to generate a voltage. So what I'm going to do is I'm going to move this coil and measure its velocity. We call this the velocity mode. I measure its velocity and I measure the voltage. So as I move it, it generates a voltage, see? And I measure the voltage and I measure the velocity. That's called velocity mode. And that turns out to be all the information I need to get the information about the magnetic field strength and where the current goes and all that, just measuring that velocity mode. Then I just do the other part of the experiment, the weighing mode. I measure the force and I'm done. So here's the deal. The mass, the force, mass times gravity is the force, the thing I'm trying to measure, that I get from the weighing mode, times the velocity that I get from the velocity mode, has got to be equal to the current that I got in the weighing mode, the thing that made the coil balance out this gravitational force, times the voltage I got from the velocity mode. When I was moving the coil at this velocity v, it generated this voltage v. Those two things have to be the same. Why? because this term, force times velocity, is mechanical power. And this thing, current times voltage, is electrical power. And so I can solve this for the mass, and this tells me what the mass is. It's the current times the voltage divided by the acceleration of gravity times the velocity. That's what I was trying to get, is a way of getting mass. But wait a minute. You said this was going to involve Planck's constant. How does that come in? And the answer is that, let's see, I just got to see how well I'm doing in time. That's great. How does this relate to Planck's constant? And it relates to Planck's constant because there's a way of making electrical measurements that are quantum. And those ways of making electrical measurements are due to these two gentlemen that you see here in this photograph with me. This is Brian Josephson. Brian Josephson came up with a thing called the Josephson effect, which says that if I've got two superconductors and I put them close to each other with a little thin layer of insulator between them, that the voltage across that junction will produce a frequency, and the ratio of the voltage to the frequency is 2e over h, where E is the charge of the electron and h is Planck's constant. And then Klaus von Klitzing said that if I take a two-dimensional layer of semiconductor with electrons in it, and I put some current through it, that it'll generate a voltage in the direction perpendicular to the current, what we call a Hall voltage. And the ratio of that current to that voltage will, or the voltage to the current, will be what we call the von Klitzing resistance, which is h over e squared, where again, h is Planck's constant and e is the charge of the electron. So now, this is just a cartoon showing how we make these electrical measurements. We put current through a resistor. The resistor is measured in units of h over e squared. We measure the voltage across that resistor, which is measured in units of h over 2e. This makes the current proportional to e. And when we measure the voltage, as I said, it's proportional to h over 2e. The current is that thing that I just showed you, the voltage divided by the resistance. And so it all works out with the current being proportional to E. It cancels out the E here, and the mass is proportional to H, just like I promised. Okay, that was a little bit quick. But one of my principles is you should never do algebra in public. So if you want to go through this a little bit more slowly, I'm happy to do that later. But the point is that if we use the Josephson effect to measure voltage, and if we use the von Klitzing effect, the quantum Hall effect, to measure resistance, then we automatically get mass in kilograms in terms of Planck's constant. So once we've defined Planck's constant, we've got mass. And these balances, here's a photograph of one of those balances at Nist. This thing can measure a kilogram, can do what we call realize the kilogram, that is, bring into reality the definition of the kilogram to about a part in 10 to the eighth, which is better than the changes that we're seeing in kilograms due to, well, we don't really know what it's due to. I'm just going to call it dirt. But maybe now that we've got a stable mass standard, we can start to figure out what these changes are due to. Here's a photograph of some of the heroes who have made these measurements at Nist. They are so confident in their measurement that they have tattooed the value of Planck's constant along with the other constants that are part of this redefinition. They have tattooed them onto their forearms. They take metrology seriously. Just like those ancient Egyptians, they really are serious. Now, one of the beautiful features of defining mass by using Planck's constant is that we don't tell you how you should do the mass realization. You could use the Kibble balance, which these heroes here have done. They use this wonderful device and are realizing the kilogram to a part in 10 to the eighth. But that's not the only way. Here's another way, which is very different. Imagine an atom. So here's my cartoon atom. I shine light on the atom. I imagine the atom absorbs one photon, one particle of light. Now, I can measure the frequency of the light. And I know that the energy of that light is Planck's constant times that frequency. And that energy, when it's absorbed by the atom, is going to make the atom change its state. The electron is going to orbit further from the nucleus, and that's what we call an excited state of the atom. So that's illustrated by having this circle go from down here to up here. So the atom is now in an excited state. That's where the energy went. But this photon also carries momentum. That means it can push on stuff. So when it's absorbed by the atom, it means the atom gets a kick, and it's now moving with a velocity. And just by applying the law of conservation of momentum, that the momentum before has to be equal to momentum after, I can calculate what that velocity is. It's Planck's constant divided by the mass divided by the wavelength. Now, the wavelength is easy to measure. Planck's constant is now defined. So I can solve this. Oh, and it turns out that the velocity is pretty easy to measure too. So I solve for mass, and I now know what the mass of the atom is in kilograms. Think about that. We often talk about what the mass of atoms are in atomic mass units. This is the mass of the atom in kilograms. Okay? Now, I can then take, usually this is an atom like rubidium. I can measure the ratio of the mass of rubidium to the mass of silicon, a very common element. Sand is made up of silicon dioxide. You can purify that silicon and make out of that purified silicon a sphere. You can see about how big it is. And this sphere is so perfectly spherical that it is the most spherical object that has ever been made. And it is a perfect crystal of silicon as well. There are no defects in it. So that means you can measure, using X-rays, you can measure what the distance between the atoms is. And then when you measure the size of this thing, using your standard of length, the wavelength of light, you know how many atoms there are in this cylinder. And that means you know how much its mass is. So here is another completely different way of getting mass from the definition of Planck's constant. That is, you define Planck's constant, and this becomes a way of measuring mass. And all over the world, laboratories like Nist's have been making measurements with the Kibble balance, making measurements with these silicon spheres. And when everybody agreed, they finally decided to change the definition. And while they were at it, they decided to change the definition of the Ampere. Before 2 years ago, the definition of the Ampere was, it was the current which, when you put it through two long straight wires, a meter apart, would produce a force of 2 times 10 to the minus 7 newtons per meter. A newton is about the force of 100 grams in Earth's gravity. A pretty small force. Not very easy to measure, and that was one of the problems. Now we have a new definition of the meter. We've defined the charge of the electron. So the Ampere is now defined as being a certain number of electrons per second. And the beauty of this is we now have an exact definition of what the charge of the electron is. We have an exact definition of what Planck's constant is. It means that Josephson's constant, 2e over h in hertz per volt, and von Klitzing's constant, h over e squared in ohms, are now exact and allow us to do electrical metrology exactly using these defined constants of nature. And besides that, the mole. It used to be the mole was the amount of substance that had a number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. And now it's just a number. What this means is we have defined Avogadro's number. And finally, the Kelvin, unit of temperature. It used to be that the Kelvin was 1 over 273.16 of the triple point of water, a fixed point in a substance that's easily available. But it wasn't so easy to make those measurements. And now we have defined the Kelvin by defining Boltzmann's constant. What is Boltzmann's constant? It's the quantity which, when you multiply it by the temperature, tells you what the energy of the atoms and molecules are that are moving around with thermal motion. So if I've got some substance like a gas, and I want to know what its temperature is, all I have to do is to measure the velocity of those atoms that are moving around. And knowing what Boltzmann's constant is, that tells me their temperature. So it's a new way of thinking about what the temperature is. So the French Revolution brought us the meter. It brought us the kilogram, the meter as a new unit of length, the kilogram as a measure of mass, something that was in the spirit of liberty, equality, and fraternity of the French Revolution. And now, 2 years ago, on the anniversary of the signing of the International Treaty of the Meter, we've had the biggest revolution in measurement units since the French Revolution. And this wonderful painting of Delacroix, of liberty leading the people, symbolizes the fact that the world is finally free of artifact standards of measurement. No standard meter, no standard kilogram. It's all based on fundamental constants of nature. All of the base units are now tied to some constant of nature. We have, it seems, finally realized the dream of the French revolutionaries to find a system of units that is good for all time and for all people. And with that in hand, with these measurements that made it clear that these redefinitions could be made, on the 16th of November, 2018, the international community gathered to decide to make this change that would become effective on the 20th of May of 2019. So at the 26th General Conference of Weights and Measures, we had the vote of all the countries in the world who have signed the Treaty of the Meter to decide to make these changes. And here is what they showed right after that unanimous vote.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have my special. Lo logramos.
那些玻璃，
我们做到了。
Biz bundan ayrıldık.
Proton die.
вызвано жасады. Это из Унсфлойца.
Вы сделали это.
Tasarım.
Ее убирай.
Америка диа.
Мы smo to učinili. Dokázali jsme to.
Angasna.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Bazalto.
Congratulazioni.
Siate le lavorisce.
Selamat sukses.
Parabéns.
Ongela. Omedetou.
Ama buydu.
Onek se olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Today, when I see that movie, I still get emotional because 60 countries from around the world agreed unanimously to make a revolutionary change, a change which, as you heard, would allow accurate and precise measurements anytime, anywhere. If we were in communication with an alien species on another star on another planet, we would be able to tell them what a meter and a kilogram and a second and a Kelvin are. We would not have been able to do that in the 19th century because things were based on artifacts. But now nothing is based on an artifact. We have this new system of units that is good for all time, for all people. Or is it? Because time itself is still tied not to a universal constant of nature, but to a specific atom, namely cesium. And the trouble we have right now is that there are other atoms that provide a superior technology to the atomic clocks based on cesium. We now have optical frequency standards that, instead of operating at the microwave frequency that cesium clocks do, operate at optical frequencies of a few times 10 to the 14 hertz and are working 2 orders of magnitude better than the cesium clock. And so it seems that we still have something to do. We still need to deal with the future of time, and just exactly what will happen is something that is under serious discussion right now. So the future of time, only time will tell. And now we've come to the end, but it's not really the end because we still have to redefine the second. Thank you very much for your attention.
Okay, thank you, Dr. Phillips, for that inspiring talk and journey through the standardization and the removal of artifacts in our measurement basis. So now is the time for the open question and answer session. And so we've gotten some questions from the chat. Some people have submitted questions by email. And so I will kick this off by asking a question that you kind of alluded to, but was asked very early on in your talk, which was, given the limitations of the cesium standard, would it make sense to define time based on a physical constant as well? Or do we have to have at least one base quantity based on experimental measurement? And this comes from Xinqing Tang.
Yeah, well, so it's a wonderful question. It has so many layers. I'm so glad that you asked this question. So first of all, let me say that when we base our measurements on a physical constant, it's still an experimentally based definition. Okay, we still have to do an experiment to realize the definition. It's just that the experiment, for example, that we used to call measuring the speed of light is now called realizing the meter. Okay, so whether it was for the cesium atom and time, right now when we make a cesium clock, we call it realizing the second. If we were to have a different definition, let's say, for example, we were to define the Rydberg constant, that would be the kind of thing that I think the question is suggesting. The Rydberg constant is a universal constant of nature that sets the energy scale for energy levels in atoms. Okay? It would be something like using the speed of light instead of using the wavelength of a particular atom's light. The trouble is that we don't understand how to go from the definition of the Rydberg constant. That is, let's say we fix the value of the Rydberg constant. We don't know well enough how to go from that number to the energy levels in an atom. And that's because there are all sorts of funny corrections, like how big the nucleus is. And you might have heard in the news that there's a kind of a disagreement about how big the proton is. This means that we can't use the Rydberg constant. And so we've made the cesium atom the standard, but it's not the best standard. It turns out there are other atoms. But even if we redefine the second in terms of those other atoms, my favorite is strontium, by the way. Let's say sometime in the future, we redefine the second in terms of the strontium atom. There still may be a new technology that comes along, maybe measuring the frequency of gamma rays, that allows us to do even better than strontium. So the question actually really puts the finger on what the problem is. As long as we make it specific to a given atom, we're never going to be sure that there isn't going to be a new technology. But with time, we don't seem to have that option that we did with length and with mass to define it in terms of a fundamental constant, because we just don't have the tools to turn that definition of a fundamental constant into a realization of the second. So we wish we could do it, but we can't. I'm not going to say we never will be able to. Maybe we'll get smarter in the future. But for the moment, we can't do it.
Okay, thank you. So another question that was asked that's intriguing is, maybe the best way to discover new physics is to discover that one of the constants of nature is not really constant. Yeah. Are we screwing ourselves with this revolution?
What a great question. What a great question. I'm so happy. Okay, so here's the deal. it's absolutely true that one of the best ways of looking for new physics would be to see if the fundamental constants of nature change. But my claim is, and I'll tell you why I make this claim, the only constants for which it makes sense to say that they change are constants that have no units. So when we define units by defining a constant, we're not dealing with the constants that really matter. If I were to find that the speed of light changed, well, first of all, I can't. I cannot find that the speed of light changed. It would be illegal for the speed of light to change because the speed of light is defined by law. So it's not possible for the speed of light to change. So what would be interesting? The fine structure constant. The fine structure constant is a dimensionless constant. It's approximately equal to 1 over 137, and it's something that gives a dimensionless measure of how strong electromagnetic forces are. Now, how could I find out whether it changes? Well, it turns out that certain energy levels in certain atoms depend upon the fine structure constant in different ways. So if I made 2 atomic clocks, one, say, based on strontium, remember strontium is my favorite right at the moment, another one based on ytterbium, which is another really good one, okay, and another one based on aluminum ions, which is another really good one, and put those clocks next to each other in a laboratory and measured their ratio over a long period of time, if those ratios changed, then I've done exactly what the questioner was asking. I've seen a change of a fundamental constant with time. And that would indicate that there's something about physics that we don't yet understand. But measuring the speed of light is not the right thing to do because it can't change just by the nature of the way we've decided to set up our system of measurement. Here's another way of thinking about it. In the SI system, the fine structure constant, this thing that's a dimensionless number that's equal to about 1 over 137, is equal to E squared over 4 pi epsilon naught h bar c. Epsilon naught is called the permittivity of free space, or the permittivity of vacuum. E, you know what it is. It's the charge on the electron. H is Planck's constant, and C is the speed of light. That's what the fine structure constant is, and all the units cancel out. Now, before the 20th of May, we knew what C was, and we knew what epsilon naught was. Epsilon naught was a defined quantity, okay? And E and H were not. So if you'd seen that the fine structure constant had changed, you would have to ascribe it to a change in E and H. E or H or both. But after the 20th of May, we know what E and H are, we know what C is, and we no longer know what epsilon naught is. So after the 20th of May, if you saw the fine structure constant change, you would have to ascribe it to epsilon naught. Well, that doesn't make any sense. The date on which I ask the question shouldn't tell me which constant was changing. The only thing that makes sense is to say the fine structure constant changed, not that E or H or epsilon naught changed or C, but only that the fine structure constant changed. Now, let me say the following. Not everyone agrees with me on this question. Everybody who is right thinking, of course, agrees with me on this question, but I want to point out that there are smart people who don't agree. I don't know why. I've never been able to understand their arguments, but they don't all agree. Most people do, but, you know, this is why we have discussions.
Okay, so another question is, what prevents SI from adopting the simpler CGS form of Coulomb's law and the Biot-Savart law, especially if we have fixed the definition of the speed of light?
Yeah. Well, right. Well, I think this is a matter of taste, whether we're going to use the CGS definition. Now, one of the problems is you got to be careful about the CGS definitions, because if you start to use electromagnetic units and electrostatic units, sometimes the units that you're using can become obscure, and the question of what units things are being written in can become ambiguous. So you got to be careful about your stat coulombs and your stat volts and things like that. But apart from that, it's really just a matter of taste. My own taste is I would rather have Maxwell's equations be simple than to have Coulomb's law be simple. So for those of you who don't know what I'm talking about, the force between two charges in one system of units is Q1, Q2 over R squared, the distance between the two charges, in one system of units. But in another system of units, it's 1 over 4 pi epsilon naught times the Q1, Q2 over R squared. And that sounds like it's more complicated. But you gain something by simplifying Maxwell's equations. And to me, Maxwell's equations are more fundamental. And so I'd rather make Maxwell's equations simple, but really it's a matter of taste. And given the fact that the international community has decided on the SI as being the measurement system, and that there's a reasonably good argument based on taste for choosing that in electromagnetic units, then why not? It doesn't matter for anything else.
Great, thank you. So switching gears a little bit, this is a question from Lynn Barrick, which is, what applications do you envision for your work in the next 5 to 10 years, or in terms of the applications or impact of precision measurement?
Right. Well, one of the things, of course, is just sort of a philosophical point. We now have a standard of mass that is not going to change. Before, we were relying on a standard of mass that could change, and apparently did change. So that's just not tolerable. But that's sort of a philosophical point. Another point is that the other definitions are now based on atomic features. That is, the Ampere is a certain number of electrons per second. That just feels a lot more modern than something based on forces between current-carrying wires. And in the same way, the unit of temperature is based on the energy of the atoms and molecules that make up the substance. So philosophically, it's just a prettier system. But it turns out there are some practical applications as well. It turns out that the new way of defining mass makes it easier to measure small masses. Why is this? Well, imagine that I wanted to measure something that was on the order of a milligram. How would I go about doing that? Well, the definition is based on a kilogram. So I've got this hunk of metal that's a kilogram. How do I find out what a milligram is? Well, you could imagine one way of doing it would be to make 10 100-gram masses, approximately 100 grams, put them all on one side of the balance, make sure that the sum of those equaled the kilogram, then compare each of the 100-gram masses to each other and find out how they were different. And now you've got something that's 100 grams, but you've lost some accuracy in the process because you had to do all those extra measurements. Then you do it again to get to 10 grams. And then you do it again to get to 1 gram and to 100 milligrams and 10 milligrams and finally 1 milligram. And you've lost a tremendous amount of accuracy in the process. You don't have to do that with the new definition. All you have to do is dial up a different current, and it's easy to measure that. So measuring small masses is being revolutionized. And in fact, there's already devices being made for measuring 1 gram and smaller masses better than was possible with the old way of doing things. So this is a practical application. And there's a lot of things where you want to know small masses.
Great. And so some people are aware of your background in quantum computing as well. So we have some questions on that. So one question is, you said your research focuses on laser cooling. Where do you see applications of laser cooling taking us? I'm particularly interested in applications for quantum computing.
Right. Well, okay, so I should spend 1 minute saying what quantum computing is. So I think most people understand that the computers that we have today, I'm going to call those classical computers, process information that is stored and processed digitally. That is, somewhere in the computer, there are physical things that represent zeros and ones. That binary information is the way we process information in our computers. And quantum information also has a binary, or typically has a binary approach, except the things that are zeros and ones, instead of being like in a computer, it might be a transistor that's turned on and off, or it might be a spot on a CD that's burned or not burned, or a place on a magnetic disk that is magnetized one way or the other. Instead of that, the quantum bit that can be either 0 or 1 is something like an individual atom that has an electron that has the spin of the electron pointing one way or pointing the other way. And the beauty of this is that in quantum mechanics, something really weird can happen. In a computer, any bit that you have has got to be either 0 or 1. There's no ambiguity about that. But in a quantum computer, this quantum bit, we call them qubits, can be both 0 and 1 at the same time. In other words, there's an ambiguity about what it is. It's not that it's one or the other and we don't know it. It's that before we measure it, it actually is both things, or it has the potential to become both things. Now, you might think that's a disaster because now I don't know anything. But it turns out that there are certain kinds of problems that work a lot better when you process the information that way. And so where does laser cooling come in? Well, in order to use atoms to be these kind of quantum bits, they have to be really, really cold. Because if they're hot, then we can't restrict the state of the atoms to just 2 states. You know, they'll have all kinds of other states and it'll be a mess. And so I've got to cool the atoms down before I can make them into qubits. And then if I can make them into qubits, maybe I can do calculations that are essentially impossible to do. But I happen to know that you are also an expert in this field. So maybe you would like to add a little bit more to this answer.
So I think I'm going to pass because I think people
Oh, come on. Let's talk about NV centers or some other kinds of quantum defects in solids.
Yes. So laser cooling for the qubits is going to be very, very important for atoms and ions systems. But there are qubits that are out there that are already trapped and have astonishingly long, not as long as atoms and ions, but astonishingly long coherence times, just being trapped in solids. They still have to be cooled. Qubits typically have to be cooled at least to liquid helium temperatures, which is 4 Kelvin, but this is orders and orders of magnitude hotter than the types of systems that you have pioneered.
Yeah, and so these look beautifully attractive for doing these kinds of things.
So the next question, we're going to switch gears a little bit. You mentioned a lot of constants that were defining constants of the International System of Units in your talk.
Yep.
And you left one out.
Okay.
Can you? So the one for luminous efficacy. What is the story behind this one?
Well, the story is kind of sordid, I'm afraid. So, so I deliberately left out a discussion of luminous efficacy because most of the time we don't like to talk about it because it's not exactly a constant of nature. It has to do with the way in which people perceive the brightness of light. So we have defined luminous efficacy so that a certain amount of light of a certain color measured in watts per square meter. So we have an intensity of light of a certain color. And we say that that number of watts per square meter looks like a certain number of lumens. And the idea is that people will perceive some other color of light or some other mixture of colors of light, like white light from a light bulb, will perceive it to have the same intensity. So that when you go and buy a light bulb, you'll know how bright it is because they advertise how many lumens it is. Okay? And that lumens is based on this idea that a certain amount of green light looks the same brightness as, any number of other colors of light. And then we have to rely on the vision curve, which turns out to be not too bad. That is, people all over the world have pretty much the same sensitivity in their eyes. But we don't like to talk about things that are related to the properties of human beings. We really like to think about the properties of inanimate physical space. And so the candela and the lumen are things that we just as soon leave out of the discussion. So that's the sordid story of the candela and the lumen.
So the follow-up was if there's any possibility to deem it redundant, if it's something we don't want to talk about.
So one possibility is to demote it, to make it so that it is not a base unit anymore, that it is another unit that we use with the SI, and that everybody agrees what it is, but we don't call it a base unit. That would be one possibility, but that would make all the people who make light bulbs upset, and so that's not likely to happen anytime soon.
Thank you for that backstory. So again, switching gears a little bit, I saw that you're a founding signatory for the Trust Science Pledge. Have you seen a change in how Americans view science during your scientific career?
Well, so that's a very touchy subject. And of course, not being a sociologist, it's a little bit hard for me to give an authoritative answer to that kind of question. So anything that I would say would be based on, sort of anecdotal evidence rather than hard evidence. But I do have the impression that people today are less trusting in the statements of scientists than they used to be. And I think the same is true of any number of other professions. I think that people are less trusting of their physicians than they used to be, that they're less trusting of their politicians or their bankers than they used to be. So it may be that this lack of trust in science is part of a larger movement of not trusting things as much. Now, when it comes to trusting your investment advisor, for example, you may have very good reasons for not trusting your investment advisor, especially if that advisor makes money by advising you to invest in certain kinds of things. But science doesn't work that way. And I think that a lot of the mistrust in science comes from a lack of understanding of how science works. So today you hear people say, how can I trust scientists? They keep changing their minds. That's exactly why you can trust scientists, because when the evidence changes, they change their minds. Whereas in many other fields of human endeavor, when the evidence changes, people do not change their opinions. And so I think this lack of understanding of how science works is something that we should correct. And what's the right way to correct it? Well, the obvious thing is that we educate children better. But, it's not always clear that that education works. So I don't know for sure. I'm just not an expert in that kind of thing. So I do the best I can with education too.
Okay, great. So I don't think we'll go down. That was a loaded comment at the end about education. I think we won't go down that path and turn back towards physics for our last few minutes. So one more question is if you had any thoughts. So you talked about different clocks and one of your favorites that it has not been adopted yet. Do you have any thoughts on the nuclear thorium?
Oh, yeah. Yeah, well, I sort of alluded to the idea that in the future that we might have something even better than optical frequency standards. So thorium, it turns out that there is this energy level in a thorium nucleus that is very close to the ground state, so close that we could access it by creating far ultraviolet light based on light that we know how to measure the frequency of. Right? Now, in order for this to work, we're going to have to excite a thorium nucleus by shining light on it. Okay? Nobody has yet done that, but people are working hard. And so I'm really eager for this to become a new direction, but I don't believe that it's going to become a viable alternative before we redefine the second in terms of an optical frequency standard. But it might be the next thing that happens after that.
Okay, great. So I think it's now time to close. I would like to thank you on behalf of the physics department and the Frontier in Physics lecture series. I would like to thank all the people that came out tonight. We were hovering around 250 participants for most of the night, and there's still 165 that are hanging on for the last nuggets of knowledge that we can gain from the evening. If people have joined us on the YouTube channel and would love to hear about future Frontiers in Physics lecture series, you can email us at the email that I put in the chat. We are excited to have Nobel Laureate Donna Strickland coming next spring. And
Donna is fantastic, by the way. So
so hopefully that will be in person, and we are finalizing now our fall, which may be in person or hybrid. We are just so lucky to have you, Dr. Phillips, to make this as personable as possible and enjoyable for a very, very large number of people. So thank you so much for joining us tonight.
Well, it's been a pleasure for me. Thank you very much.